Tonight we're looking for a natural number of positive integer trying to satisfy a couple of conditions. Now, LCM stands for the least common multiple. GCD stands for the greatest common divisor. That's also sometimes called the highest common factor, I believe. In particular, I've seen this used in SMO competitions. Highest common factor, GCD mean the same thing, all right? Now, there's a result here that gets us through this problem relatively pain-free. It's you can take the product of the least common multiple with the greatest common divisor, and you actually get the product of the two numbers. Okay, you get the product of the two numbers. So let me just show you a concrete example here to make a believer out of you. If we take a equals 6 and b equals 15. Again, I'm just picking these numbers because they're easy to compute here. Okay, now we're looking for the smallest number that is a multiple of both 15 and 6, and that's clearly by inspection 30. Okay, I'm just trying to justify this rule. I'm not trying to prove it. You can prove it from the prime factorization. It's kind of a technical proof, but I'm just going to show you one example. All right, now the greatest common divisor of these same two numbers is 3. That's very clear. 3 is a divisor of 6, 3 is a divisor of 15, and it's the largest divisor of both of them combined. Okay, common, that's where common comes in. Now notice that is equal to 6 times 15, right? They're both equal to 90, right? So again, this does not a proof make, but it convinces you that this may be a useful tool, and it's probably true. So we're going to stick to it as a fact for now, not going to attempt to prove it rigorously. All right, let's move along. All right, now we're going to just use this result with unknowns, okay? We know that the LCM of n, 154 times the GCD of n, 154 is equal to 154 times n based on this result right here, okay? Now, we're given the LCM of the two numbers. Here you got this 5-digit number and then a 2-digit number right here. You would expect this to be a smaller number than this number, all right? Now, so let's keep going. Now, so again, the given conditions in this fact right here imply this statement. All right, that's real clear just by substituting, okay? Now, probably the most difficult part is just to find the prime factorizations. I think that's almost a requirement here if you don't want to use a calculator. You may wonder, it's believable that a power of 2 would be a factor of 11,704 since 11,704 is even, right? What about 7? Y'all, you may have heard of that. There's a nice divisibility rule for 7. If you take the last digit of any number, multiply it by 2 and subtract it from the previous digits, so that would be, in this case, 1170 times 2 times 4. And y'all, what are we doing? We're checking to see if this is divisible by 7. It's not divisible by 5, right? So we're checking the next prime number. Okay, now notice, what is that? That's 1162. Okay, now again, it's not, I don't know if this is divisible by 7, so we can rinse and repeat here. This leads to, okay, if you multiply by, this would be 116, and I'll just use an arrow here. It's not equal, but 116 minus 2 times 2, okay, equals 112. All right, and this is, most of us can calculate this in our head. This is 7 times 16, right? 7 times 16 is 112. 7 times 16 is 70 plus 42, which is 112. Okay, so that's where that 7 came from, right? And y'all, there's a divisibility test for 11 also, and then you just have to grind it out for 19 once you get these factors. Okay, so I'm not claiming this was easy, but I just wanted to show you there are divisibility tests to help you find the prime factorizations of large numbers such as this 5-digit number, okay? Now 2 times 7 is 14, that's easy enough. And of course 154 is not a bad computation. That's 2 times 7 times 11. 11 times 14 is 140 plus 14 is 154, right? Now so we're just about done. Okay, the 2 times 7 cancels with the 2 times 7 right here. This 11 will cancel with this 11 right here, right? All right, and so all that we have left, folks, is 2 cubed. Now, I don't know how that got underlined, but that's included. We have 2 cubed times 7 times 19. Okay, folks, and I did the multiply on that for you, and that came out to be 1,064. I went ahead and just used a calculator for that. Technically, in a competition, you wouldn't be able to use a calculator, but I went ahead. And so we get equals to n. Okay, folks. See, all of these factors canceled out, so we have n equals to whatever's left here. And again, this 2 times 7 canceled with this 2 times 7. This 11 canceled with this 11. And I didn't mean to let me erase that if I can. Yeah, that shouldn't have got underlined. So what we have left here is this 2 cubed is a survivor, this 7 is a survivor, and this 19 is a survivor. And so we get n equals to 1,064. And y'all, with the size of these numbers, I think this would have been very difficult to find. If you just, if you just look at this problem naively and you go, what n would satisfy this? Who knows? If the numbers are smaller, you can often do this kind of thing by inspection. But the size of the least common multiple alone is enough to make it a daunting task to actually figure it out manually, unless you write down the canonical form or the prime factorization. So anyway, hope you enjoyed that. And this is the major result that got the job done for us. Thank you for viewing.